Okay, for those of you who are here, welcome. So they'll just be like a regular meeting. So this week you'll be going over the DIRT experiment, experiment 11, synthesis of 2-chloro-2-methyl butane. So this chemistry should be kind of like review. It was an SN1 reaction that you encountered earlier this quarter and probably last quarter too. Okay. Doesn't. All right, so I know because of the power out, there are some people cannot submit stuff online because they have no power. So for everyone, if you didn't take the pre-lab quiz, please take and submit it whenever you can, preferably before the lab report is due, so you get points for it. Anything after the lab report is due will be considered late. The experiment for experiment 9 will be due on Saturday. So I decided to give everyone a 48-hour extension just because if people cannot submit their report on time. So if you cannot submit your report on time, you must let me know. And if it's because of the power outage, I will give you until a 48-hour extension. So until Saturday before midnight. Okay, experiment 11. So just a reminder, everyone just complete the activity and submit the Google form at the end. So the Google form will always be at the last page of the activity. So the experiment should be open, so you should be able to do that. So do that before the due date for the lab report, which will be due next Thursday before midnight. Okay, that's the agenda. Okay, so today we're going over the reaction of 2-methyl-2-butanol and what happens when we react it with hydrochloric acid. Well, we should get a substitution reaction, and we should be able to, our product should be 2-chloro-2-methyl-butane, and then we get water as a byproduct. Whoops. Okay, so the learning objectives for this experiment is you're going to learn how to set up a refluxing reaction, not refluxing reaction, but set up a reflux apparatus, distillation, and then nucleophilic substitution. So the reflux, I think during the distillation, I think you do get some reaction to maybe occur, but I don't think so. So I think what I meant to say is setting up a reflux, but you can use a reflux to do reactions. So what we're learning today, you can also apply to like chemical reactions. Distillation, we're going to set up a distillation apparatus, and then nucleophilic substitution, that's the reaction we're happening today. Talk about the mechanism. Is it SN1 or is it SN2? And we'll talk in detail about the mechanism. Okay, the setup here is distillation is a method to purify liquids by boiling point. So if we have a mixture of liquids, we can separate it by 2 different boiling points. So if we have if we just heat up the flask to a certain temperature, we can separate the 2 liquids. Because the lighter boiling point, the lower boiling point, the lower boiling point will separate and will enter the vapor phase first, allowing us to collect it at the end. So this setup is kind of similar to what you will encounter in the lab. So let's go over some of these points. Here you have your heating source. So that's the heating apparatus. In this case, in this experiment, you're not going to use what we call a sand or oil bath. You're going to be using an aluminum block. So that's how you heat up your flask. Your flask will sit on the aluminum block, and that's how it will be heated. Here you have 3 is your still head. It's called a still head, or you could call it like a column. It's how your vapor will rise up and transfer over to the other flask. So you see here in this column, it has something. It has some plates. So that's like for fractional distillation, which is what we're not doing that today. But if you were to have 2 liquids with similar boiling points, we would use a fractionating column like this to separate the 2 liquids. But in our case, we don't need to do that because our boiling points of the alcohol and product are very different. So it'll be easy to separate. So notice here our thermometer, we're going to put it slightly below the side arm here. So this is what we call the side arm in our apparatus, but here is a water condenser. So a water condenser is just the cooling part of the distillation, where we cool down the vapor and condense it back to liquid, and we can collect our pure liquid in this flask right here. So it's very similar to our setup. So we put the thermometer just below the sidearm so we can measure the temperature of the vapor, and that should tell us that the temperature should be at near the boiling point of the more volatile or lower boiling liquid. Okay, so then 5 is a condenser. I talked about that. Usually you fill this in with water. 1 water comes in, and 1 water goes in, and then 1 water line will go out. So as you can imagine, this is a very water expensive process. So these we're trying to phase out water condensers because they waste a lot of water. So if you have running water, you're going to be wasting a lot of it just trying to cool down this apparatus. So things we do now is we have static liquid condensers, where we just have a liquid that's self-contained and we're not wasting any. Or we have like what we call like a fish tank, or like a bucket of water, where we just cycle in water in like a reservoir, so we're not wasting water continuously. And then these other parts are just a little bit extra things. Don't worry about like this outer part here. That's a gas inlet. So there's many types of distillations. If we were to do a vacuum distillation, you will hook this up to a vacuum. And those kind of distillations have unique uses, but not for our case. Okay. So usually when you do a distillation, you'll have something in the flask right here. Your liquid, you'll have something that looks like a little chip right here. You can either put boiling chips to help the distillation proceed more smoothly, or you can have what we call a mechanical stirrer, like a Teflon stir bar, that helps stir the liquid and makes the distillation proceed much more smoothly and without what we call bumping, where the liquid violently bumps because it's trying to evaporate. So if you don't stir it uniformly, bumping can occur, and that could splash your liquid. It's very undesirable because it can the force of the bumping can shoot the liquid all the way up the column, and that may transfer some of your undesired material or product that you don't want. So it may contaminate the product that you're trying to obtain. Okay, so this was a nice. So this is distillation is a very old technique. It's from this book right here. Okay, so that's distillation. Brief summary of it. Okay, so what about the reaction mechanism? So remember, this is the SN1 process. We learned about SN1 reactions with alcohols. We convert it to a good leaving group, protonate the alcohol to form the alkyl oxonium. Then it leaves to form the stable tertiary carbocation, which then chloride will stick around and quickly quenched or react with the carbocation to form your product right here. Okay, If there's any questions, just let me know, because we have a few people here, more like one right now. Okay, so what about the formation of alkene? So if you remember, like Dr. Levins talked about the formation of the alkene, and you know why we don't see it in these types of reactions, and it's because even though it forms, it can form as a byproduct. You get both the minor and major, but it'll mostly be the major tertiary. No, sorry, not tertiary, triply substituted alkene, because that's thermodynamically more stable, based on their energetics. So triply substituted alkene will be the more favored product thermodynamically, so it will form as the major product. So even though we formed alkene, it's unstable to the reaction conditions because you have an excess of hydrochloric acid. So the HCl will just react right away with these alkenes, and if you react with this one or this alkene, you'll get the same product because it prefers to form the carbocation on the tertiary position. So it does not matter what alkene you have, you always get the same product. And this is the product we got in the SN1 reaction. So even though the alkene forms at the end, it should all convert to the 2-chloro 2-methyl butane. So my question for you is, can you draw the mechanism? You may encounter this on the post-lab, so keep that in mind. And also, when you see the distillation, you'll notice that the distillation doesn't even start until like I think 79 degrees or somewhere around there. And you notice that the boiling point of the alkene is only 39. It's 39 degrees Celsius. So if there was in fact some alkene present, you'll probably notice the distillation would occur at a much lower temperature than like 79 degrees. So the fact that we probably don't see that is probably is due to the alkene just being converted to the chloroalkane. But you'll notice when you watch the video. So hopefully think about these questions after you watch the video and when you're doing the post lab. Okay, whoops, I forgot to put an animation there. So the distillation experiment. So let's ask this question: what vapor will be enriched in the lower or higher boiling compound? So whenever we have a mixture of liquids, the more volatile component or the least boiling component will always be present in the vapor at the higher fraction. So which of our substances is our lower/higher boiling compound? So we have to compare the product and the reactant. And you know that our 2-chloro 2-methyl butane has a much lower boiling point than 2-methyl-2-butanol, and that's because alcohols, they tend to have higher boiling points than haloalkanes due to hydrogen bonding interactions among its molecules. Okay, so now let's talk about the extraction part of the experiment. It's too bad you're not able to do this technique in lab, so you won't have this under your belt. But just watching it, I think, is still good. It's better than not learning it, right? So so in the future, you can actually demonstrate this technique if you ever go into another, chemistry lab. So which layer is which? So when we extract our organic layer, you're going to use water to kind of wash it. So which layer will be your bottom layer? So no, which layer will be your organic and which layer will be your aqueous? So where will your water be and where will your product be in this extraction? So here we have a separatory funnel. That's how we do liquid extractions. So like which layer will it be? So I won't ask questions because there's not many people here, but so let's just go forward. So it turns out you have to look at the density of the two materials. So 2-chloro-2-butane is less dense than water, so it will appear as the top layer. and water has a much greater density than 2-chlorobutane, so it will sit at the bottom. So the more dense material will always sink to the bottom due to gravity. And so we identified the layers. So which layer, how can you test the layers? So how can you, like, if you don't know and you didn't have this information with you on hand, how can you tell which layer is which? Well, you can do a little test where you take a few drops of water and add it to the separatory funnel, and then very carefully, as you drop the liquid, the drops of water in the flask, you're going to look how the layers behave. So if you see something trickling down to the bottom layer, that means it's going to add to the bottom. So that means the bottom layer is your aqueous phase. So that's what you would do. Add a few drops of water and then observe which layer it goes to. And if you see it adding to the top layer, that means it's going to be on the top layer instead of the bottom. So that's how you would tell. Yeah. Okay, let's go on. Let's move on. So the thing about this technique is that a lot of people can mess up. So their technique is very important here. So if you get the wrong layer and you draw the other layer out by mistake, you have to start over. So it's very important that you save both layers so that you don't have to start over, and you kind of keep track where everything goes, because big part of chemistry is understanding what happened and like where your material is. So you should always be making educated guesses using scientific reason when working through these procedures. So you should always know like what's happening in your flask, like what reactions occurring, and like keep track of like what's happening, and so you'll never be lost or use guesswork when doing chemistry. So that's a good skill to have. So it's always important to keep both layers. Okay. So I think we're almost done here. Just a few more slides. So another tricky concept is washing. What do we mean by washing? Like when you wash clothes, right? You remove the dirt and stains from your clothes. Sort of the same thing here, but with liquids. So what you're doing is that you ensure that everything in the organic layer is organic. So we're going to remove the excess HCl that may be present in the organic layer, because we don't want that when we're trying to distill. That can complicate things. So we're going to remove the excess HCl, and we're going to do this washing procedure 3 times, because it's all based on solubility between the layers. So if we HCl will be more soluble in the aqueous layer, but when we add water, undoubtedly you're not going to wash all of the HCl off. There's going to be some left in, and that's due to the partition coefficient, which is a property it's a property of how like certain compounds go into one phase versus the other in a biphasic mixture. So there's always going to be some more solubility in one layer than the other, but to ensure that you remove all of the aqueous stuff from the organic, you have to do this procedure at least 3 times. So we would do this 3 times, and you can watch that how a lot of people do that in the video, and you can see how that is done. All right, lastly, we're going to talk about drying. We're going to add something called sodium sulfate. It's a drying agent. It means it likes to absorb water. So it's kind of counterintuitive, because many students, when they see this, they're like, oh, I added the sodium sulfate, but I can't tell if it's dry or not because I still have a liquid. But the point is we're trying to remove water. So you're looking for if you have water, you usually see some fizzing action. If there's lots of water in your organic phase, fizzing action, and that's pretty much a chemical reaction of hydration of sodium sulfate, where it absorbs water. So the key here is you would add portion amounts of sodium sulfate, swirl your flask to make sure the solid absorbs the water. And if you see like any clumping, like parts of the solid is like looks hard like a rock, or like looks really solidy and not like not free flowing like sand, or like sand pretty much. Like if you look at sand and water, it's pretty free flowing. There's no clumps or anything. So you're looking for clumpiness. When there's no more clumpiness of the solid, your mixture is dry. But you would do this procedure. You let the solid dry your organic layer for about 15 to 20 minutes. And usually you'll stir it while it's doing that, but it's not necessary here. So that's drying. We add the sodium sulfate to absorb the water and remove it from any water that got into our organic layer when we were separating the layers. So separating the layers is not perfect, but you do your best to separate them completely, and then you just dry it with sodium sulfate to remove the excess water that may have gone in there when separating. Okay, so that is washing. So we're almost done here. Okay, so lastly, we're going to talk about percent yield calculations. So after distillation, so the distillation setup, read the lab manual, watch the video. There'll be a question about the setup, and you'll see the setup will tell you, will show you how the distillation is being done, and it'll be slightly different than the distillation setup I showed you earlier. So lastly, after your distillation, you're going to collect the product you collect in the vial. You're going to remove it from the ice bath. You're going to let it dry, or dry it, and then weigh it and weigh the product. So when you weigh the product, make sure you always weigh the vial and the cap and the label, if there's a label on it. And then afterwards, you weigh the same thing with the product in there, and then you can take the difference to determine the weight of product you obtained. So the weight of product you obtained, or the mass of product you obtained, sorry, the mass, that's called the yield. And then the percent yield is our experimental yield, or what we obtained right here, divided by our calculated theoretical yield multiplied by 100. So this may be a familiar concept in Gen Chem. It still applies here in lab. So I'm going to be giving you data on data, so you can do this calculation. So this data will be given to you. So use this data for the post lab to calculate the percent yield. It's probably preferable if you show your work, so I know your dinking process. But so yeah, please show your work if applicable. If you need more space, do show your work on a piece of paper and just turn it in, so we know like your dot process. And if you made a mistake, we can probably give you some partial credit. But here are the molar masses in case you need to use them. They are there. And that is it for this lab. So just remember that for the post lab for experiment 9, if you have no power, you can turn it in late. I'll accept it. Just let me know if you're going to turn in late, because there needs to be a valid excuse. And hopefully everyone who does not have power, stay safe, stay warm, and stay healthy. And we'll be back here next week. All right, everyone. See ya. That's it.